Hello class, this is lecture 5A, Colloids. In this lecture we will identify everyday uses for clay. We will define colloids and describe the various properties associated with them. We will describe various crystalline structures of phyllosilicate clays and the properties associated with each of those. And we'll identify and describe the other colloids, which include non-crystalline silicates, iron and aluminum oxides, and soil organic matter. First, let's talk about some uses for clay. So some of my favorites include claymation videos. So here's Gumby, my favorite claymation, Shaun the Sheep. And some of you might be familiar with Wallace and Gromit. So those are all examples of claymation videos. We can also use clays for clay pottery. Maybe even some folk art like these face jugs. Or we can make movies or watch movies with pottery and ghosts, or make a clay mask. We can also make building materials like clay roofing or clay shingles, bricks. We can even make ceramic knives, and we can make cosmetics. So these are all examples of products made from soil that is typically high in clay. We can also eat it. So geophagy is a term that's used to describe the practice of eating earth or soil-like substances or substrates, such as clay or chalk. And this is colloquially called white dirt. And usually what is eaten, at least as you see like with this chunk right here, it's usually very high in kaolinite. And you might think this sounds disgusting, but I bet each of you actually have done or practiced geophagy in your lifetime. One example is kaopectate. If you've ever had diarrhea and took kaopectate to fix it, the active ingredient in kaopectate used to be kaolinite. So if you've ever had diarrhea medicine, you probably had kaolinite, which is the same material that is in that so-called white dirt. Also, kaolinite is used as an ingredient in soft serve ice cream. So if you've ever eaten soft serve ice cream, I'm sure most of you have, then you have definitely ingested kaolinite. And one of the podologists in the agronomy department, he has an X-ray diffraction machine, and he actually took some soft serve ice cream and analyzed it on the X-ray diffraction machine, which tells you what minerals are present. And he got like a perfect signature of kaolinite. So soft serve ice cream includes white dirt. All right, so this term colloids is a general term used to describe small pieces of clay and organic matter. So again, these are small in size, and with a small size, they have a high surface area, and they're also highly reactive. So this is a trend that we've talked about all semester, where the smaller the particle size, the more surface area, and the more chemical reactions that occur. So small particles, if we think about the relative sizes of our soil particles, we have sands as our biggest soil size particle, 2 millimeters in diameter down to 0.05 millimeters. Silt, 0.05 down to 0.002 millimeters. And clay is less than 0.002 millimeters in diameter. So we can think of sand, if we zoom into it, as a beach ball, silt as a softball, and clay as BBs. But one thing that's important with all these is clays. Think of those BBs as being charged, so they have sort of magnetic properties. And they're also small, which gives them a large surface area. So I have a thought question for you. If we have a football field, if we add up all the surface area for the soil underneath the football field to a depth of 1.5 meters, what would that surface area end up being? And for some reference for that, colloids generally have a surface area of around 10 meters squared per gram to 800 meters squared per gram. So there's a large mass there, and it ends up being a large surface area. So I'll let you think about that for a few seconds. All right, so if we have a football field 1.5 meters in depth, that ends up being equal to the lower 48 states. So a very large land area if we add up all the surface areas of all the colloids that would be in one football field worth of soil. So we have all those surface areas, and a lot of that area is in contact with the soil solution and can allow for the exchange of cations. So with these cations, they generally absorb on the outside of these layers of clays. And so if you look at this figure, we have this clay particle, and you can think of clays, when they stack up, they sort of look like a bunch of pages in a book, where there's a front page, a back page, and then a stack of pages in the middle. And the parts that are accessible to cations are the edges of those pages and the front and back page. And so this is zooming into the edges of those pages, and we have cations like calcium and potassium and magnesium that are attached to each of those. And in this example here, we have a calcium, and again, one point with this is all these cations are vibrating. And if they happen to vibrate too far away from the cation, it opens up that location, that charge site, for another cation to swoop in and take its place. So we get this process called cation exchange, where cations are exchanging their locations on that colloid. And most of the charges on clays are negatively charged. So we can think of these colloids, these clays, as just large anions, and they're swarms. So we have these cations, and these cations are generally occur in what we call a hydrated state. So some example cations that occur commonly in soils: aluminum, calcium, magnesium, potassium, hydrogen, sodium. Those are the most common cations present. There are other cations present, but in lesser amounts. So for the sodium example, it's hydrated, meaning that it's not just a bare cation floating around in solution. It's actually hydrated and completely surrounded by water molecules. And because sodium is a cation and it has a positive charge, the part of the water that's pointing towards the cation is the part of the water that has a negative dipole moment. So H2O has two hydrogens. Hydrogens are positively charged, so they point away. The oxygen is negatively charged, and it points towards the sodium. So we have all the water molecules with the negative side pointed towards the sodium, and the positive side pointed out. And we can think of these cations swarming around, or these water molecules swarming around the sodium and the rest of the cations. And then we can think of these cations swarming around the large anion colloid like a swarm of bees trying to protect their queen. So these cations are swarming around these large stacks of clay, kind of like you see with this picture of the bees there. And they're all vibrating, just like these bees would be kind of buzzing around. All these cations are vibrating. Some of them might vibrate a little bit too far, which opens up an exchange site for another cation to swoop in and take its place. And so we can say these cations are exchangeable. And this exchange happens when they just happen to vibrate too far away. And again, this process is called cation exchange. So these cations, when we talk about this swarm of cations surrounding these colloids, sometimes you will hear it referred to as the ionic double layer. What that means is the inner layer is the anion itself, the colloid. The outer layer is the cations that are completely surrounding the colloid. So inner layer, anion, colloid, outer layer, cations. And we have a bunch of other cations that are floating around in solution. And if you look at the proportion of all the cations present, so aluminum, hydrogen, sodium, potassium, calcium, and so on, if you made a pie chart of the percentage of each of those cations, that pie chart is going to be identical for both what's in solution and what is absorbed onto the colloid. And so if we add a whole bunch of calcium, then that is going to change the equilibrium, and eventually it will kind of rebalance itself, and we'll find equilibrium between the colloid and the solution. Now there's cation exchange, but there's also anion exchange. So I said most exchange sites on these colloids are negatively charged, but there are exceptions to that. So in some cases there are positive charges, and those positive charges allow for the absorption of anions. So this is more prominent in acidic soils, so less so in neutral to alkaline soils. And these anions can be absorbed onto the positively charged sites on the colloid, just like in a similar fashion to how cations are absorbed onto the negative sites. Our common soil anions are nitrate, sulfate, and chlorine. There are other anions present, but those three are the most common ones. And again, these are exchanged similarly to how cations are exchanged. Now these colloids can absorb water, and they do that because the water is attracted to those surfaces. So we have the absorption or adhesion of water onto those surfaces, and so we have what we call matrix potential, so the attraction of water to those surfaces. And these water molecules are also attracted to the cations that are swarming around the colloid. Generally, the more surface area that we have, the more water that is absorbed, more water that's absorbed by the soil. But the caveat with this is that a lot of the water that is adhered to the surfaces of these particles, these colloids, a lot of that water is not plant available, meaning that the matrix potential of that water is so great or so negative that the water can't be sucked out of the soil and away from that colloid by a plant. The plant can't exert enough energy to get that water, so it's unavailable to the plant. Another concept is we have what we call shrink swell clays. So as water goes into the soil, some of these clays, as they wet up, will actually expand in volume, and that can cause some issues. So one example is if we get cracks in a building because the foundation's getting stressed from clays expanding, that can cause some problems, especially if we have a house with a basement. And we also can see if we have a dried up area where the soil is really cracked. A lot of times when you see a cracked surface like you see in the bottom right, that is an example of shrink swell clays, where those clays have dried up and they've shrunk, and if that area were to wet up, it would be continuous, and all those cracks would fill. The types of colloids include crystalline silicate clays, non-crystalline silicate clays, iron and aluminum oxides, and organic matter or humus. So let's talk about the crystalline silicate clays first. You'll oftentimes hear these referred to as phyllosilicate clays. So phyllo is the Greek word for leaf. So leaf clays or leaf silicate clays. And they vary quite a bit based on their composition and properties. So they have there's a variability in how much charge is associated with each of these minerals, how sticky they are, how plastic they are, and also whether they shrink or swell or not. The building blocks of these silicate minerals are the silica tetrahedron and the aluminum octahedron. So let's talk about the silica tetrahedron first. So a silicon tetrahedron, tetrahedrons are pyramid shapes, and a silicon tetrahedron has oxygens at each of the four corners and a silicon at the center. That silicon has a 4+ charge, and oxygens have a 2- charge. And so having one silicon at the center and one oxygen at each corner, there is one charge of each oxygen that's offset by the silicon at the center. And there's a remaining charge in each of those oxygens that allows that oxygen to become part of or linked to another silicon and or another or an octahedron. And so that allows for these crystals to expand in size as we have one tetrahedron with oxygens that aren't completely offset for their charge, they can absorb or become part of another tetrahedron, and it sort of builds that crystal lattice out. And in octahedrons, we have sort of a similar phenomena, but we have aluminum at the center, and that aluminum offsets a half a charge for each of these oxygens. And so we have 6 oxygens for 1 aluminum. So tetrahedrons and octahedrons. And these tetrahedrons and octahedrons will form sheets where you have one layer of tetrahedrons, one layer of octahedrons, and in some cases you might have a second layer of tetrahedrons. So we have sort of a sandwich where there's tetrahedrons on the top and bottom and octahedrons in the middle. And you can see in this diagram we have the tetrahedron showing up here with the peak pointed up towards the octahedral layer. And in the octahedral layer we have the aluminum and the oxygens, and that's set in the middle layer, or inside the sandwich. Much of the charge that occurs in these phyllosilicate clays comes from what we call isomorphic substitution. So as an octahedron forms, we can have magnesium and zinc that can take the place of Al3+ at the center of the octahedron. And that ends up having one negative charge that's unbalanced. And it also happens in tetrahedrons. So let's look at the octahedron here first, though. So we have an aluminum at the center with a 3+ charge. We have an oxygen and oxygen. And right now, all those charges are balanced, so there's a net 0 charge. But if we were to have cations of similar size, the magnesium or the zinc or iron, then we can have those cations take the place of the aluminum, but those cations only have a 2+ charge. And the end result is not all of the negative charges of the oxygens are offset, and we end up with a net negative charge for that location within the crystal structure of the clay. And so we get this charge that gets built into the crystal structure. And this does happen in tetrahedrons where we have iron or aluminum take the place of silicon. And the amount of substitution varies from clay to clay, and what particular cations can replace the center cation depends on the size of those cations. So in this figure, we show silicon for tetrahedron sheets, and so this top bracket here, the silicon goes from 0.042 for silicon, and then we have aluminum at 0.051, iron at 0.064 nanometers. And for each of those, we have a very similar size. So that means that aluminum and iron, being similar in size to silicon, can take the place of silicon inside a tetrahedron. In octahedrons, we usually have aluminum at the center, but we could have iron take its place. So iron is pretty close in size, 0.064 compared to 0.051 for aluminum. And if iron 3+ took its place, then there's no change in the charge because both aluminum 3+ and iron 3+ have the same valence. But if we have magnesium 2+, zinc 2+, or iron 2+ take the place of aluminum, because there's a change in the valence of those cations from aluminum at 3+ to the other ones at all 2+, then we end up with a net negative charge because it wouldn't offset all the negative charges of the oxygens. So what cations can take the place depends on the size, not the valence. So it depends on the size. But if the valences aren't equal, then we end up with a net charge imbalance. So tetrahedral sheets are the top 3. Octahedral sheets are generally aluminum, but that aluminum can be replaced with iron, magnesium, zinc, or iron 2+. All right, so now let's get into the types of these clays. So for for these phyllosilicate clays, a lot of times we'll describe them as 1-to-1 clays or 2-to-1 clays. So a 1-to-1 clay refers to one layer of tetrahedrons and one layer of octahedrons. And a 2-to-1 clay has two layers of tetrahedrons with one layer of octahedrons in the center. So looking at this figure below, kaolinite is our only example of a 1-to-1 clay in this figure. Smectite and vermiculite both have two layers of tetrahedrons and one layer of octahedrons. And then there's this gap in between these little sandwiches of clays where water and other cations can go in there, and as they wet up, these clays will actually spread apart and make more room for those water molecules and other cations. And then as they dry, those clays get closer together and they shrink in size. And then we have a third type that we call a 2-to-1-to-1 clay. So chlorite is an example of a 2-to-1-to-1 clay. And then both chlorite and fine-grained mica are considered non-expanding 2-to-1 clays. So they both have two layers of tetrahedron sheets for every one layer of octahedral sheets. But in both mica and chlorite, there's something in the middle between those layers of clays that prevent them from expanding when they wet up. So these are non-expanding 2-to-1 clays. So in the case of mica, there's potassium in the middle. In the case of chlorite, there's a hydroxide sheet that's in the middle. And the analogy that I like to use for describing these types of clays is Oreos. So if we have a 2-to-1 clay for like an Oreo, we have two layers of cookie and then one layer of cream. So think of the outer layers of cookies as tetrahedral sheets, and the inner layer, the cream, as the octahedral sheet. And so if we remove one of these layers of cookie, we're left with one layer of octahedral sheets, the cream, and one layer of tetrahedral sheets, the cookie. And if we have a whole bunch of those where one side of the Oreo has been removed, we can sort of think of those as 1-to-1 clays. And they don't really expand. Or we could leave them intact and there'd be like a 2-to-1, or we can kind of glue two Oreos together, and that would be like a non-expanding 2-to-1 clay. So 1-to-1 clays. So when they're stacked on top of each other, so we have an Oreo cookie and cream, we removed one of the cookies, and now we have another Oreo cookie and cream, and we can just stack those up one on top of the other, and we end up with these 1-to-1 clays. And there's hydrogen bonds that form between each pair of tetrahedral sheets and octahedral sheets. And these hydrogen bonds prevent these clays from spreading apart when they wet up, and that makes these non-expanding clays. So they're 1-to-1, meaning one layer of tetrahedrons, one layer of octahedrons, and they do not expand. Some other properties associated with 1-to-1 clays: they're easily tilled, and because they don't swell, they make for ideal material for building roadbeds, making bricks, making pottery, and so on. 2-to-1 clays, some common examples are vermiculite, and then there's a group of minerals that are called smectites, and these are kind of the most common examples of 2-to-1 clays. These layers are held loosely together, so there's no hydrogen bonds that keep these from expanding like we have for the 1-to-1 clays. In this case, we have two layers of tetrahedral sheets, one layer of an octahedral sheet, and we have this big gap in the middle that can be filled with these water and other cations. And as these wet up, that layer in between those sheets expands. And as they dry, they contract. And we end up with expansive clays that expand when they're wetted, and they contract in size when they're dry, or they shrink in size when they're dry. And the force that occurs when they're wetted up can be substantial. It's enough to destroy foundations and roads and basements and so on. And so we end up with a clay that we actually used to classify our vertisol soils. So if we need to go back and review vertisol soils, so we needed a high clay content, 50% or more, to a depth of 50 centimeters, that is shrink swell clays, like smectite or vermiculite. So vermiculite has more isomorphic substitution. So it has more cations that are substituting for the center cations in the sheets. And what that does is result in those clays being held closer to one another and not expanding quite as much. So vermiculites are less expansive than they may get for smectite. And then we get to our non-expansive 2-to-1 clays. So this includes fine-grained micas, like you see here on the left, as well as the chlorites, like you see on the right. So fine-grained micas include weathered muscovite and biotite. And the source of charge is usually a substitution of aluminum for the silicon in the tetrahedral layer. That gives a high net negative charge, and this high charge allows for potassium to kind of go into all the little gaps in between these layers. And once the potassium's there, these layers kind of collapse, and they trap that potassium for a long time until that mineral weathers. And as a result, we end up with this non-expanding clay, where it's a 2-to-1, but these layers can't be split apart because that potassium is kind of holding it together like a glue. For chlorides, instead of having potassium in the center, we have a layer of iron oxides or aluminum oxides or some other sort of oxide. And we sort of think of that as a third type of layer. And so chlorides, you'll sometimes hear being referred to as a 2-to-1-to-1 clay. So 2 layers of tetrahedral sheets, 1 layer of octahedral sheet, and a third type of layer, this hydroxide sheet. And so what prevents these from expanding is the presence of that hydroxide sheet. So these are both non-expansive 2-to-1 clays, and then chlorides we can think of as a 2-to-1-to-1 clay. We also have non-crystalline silicate clays. So these generally form from volcanic ash. So we have volcanic ash. If you think of lava or magma, it's blown out into the sky. We have all this rock material that cools so fast that there are no crystals that are allowed to form. So you don't have enough time to get the organizational structure like we see in the other types of crystalline silicates. And so there's no crystals that form, so there's a lot less organization. And we end up with a lot of tightly bound silicon, oxygen, and aluminum atoms. So kind of the building blocks of what makes our regular clay colloids. But they don't exhibit any ordered crystalline sheet. Some common examples include allophane and amogolite. And generally these silicate clays are associated with having a high amount of both positive and negative charge. So they have a high CEC and a high anion exchange capacity. And they still have a lot of surface area, so they end up with a high water holding capacity. And because they're not stacked on top of each other neatly, it's all kind of disorganized. And so generally with these ash-derived soils, with these non-crystalline silicate clays, we end up with a lot more micropores. And so we end up with a low boat density, high porosity soil that has a high amount of charge, both positive and negative. And also, these clays are generally very plastic, so you can easily mold them into whatever shape you want, but they are not sticky. So they end up being kind of very interesting clays to work with. One interesting property with these is that because they have a high amount of positive charge, that positive charge holds on to phosphorus or phosphates very tightly. And so these soils, they're very productive once we have basically filled all the positive sites with phosphates. So if we have a soil that has this type of clay, generally we have to invest a lot of money to basically saturate the soil with phosphorus. And then once that occurs, we can just fertilize like normal, and these become very productive soils. The next type of colloid is iron and aluminum oxides. So some examples include goethite, which has iron 3+, and gibbsite, which has Al3+. And so these are basically rust. So iron oxides, think of rust on a car. That also occurs in the soil. So we have iron oxides of different types that give us reds and yellows and browns, our warm colors. So that's one of our main coloring agents in the soil. The charges, these generally aren't quite as crystalline as we get for some of the phyllosilicates. They are crystalline to an extent, but there is no isomorphic substitution. So there's no kind of permanent charge that's part of these clays. So most of the charge comes from some oxyhydroxyl groups. So sort of like functional groups like we have for organic matter, but in this case, like iron oxides, where there's a bunch of oxygens that under a low pH will be protonated, and under a high pH will have an exchange site where there's a negative charge. So it's a pH-dependent charge that occurs with these oxygens that are on the soil. Some properties with these types of colloids: they are non-expansive, they're not sticky, and they're not plastic, and generally they have a low CEC. So if you remember back to Unit 1, we talked about subsurface diagnostic horizons. If we have a BT horizon, generally that BT horizon is either a argillic horizon, or if it has a really low CEC, we call it a candic horizon. And if we have a soil that has a BT horizon, but most of the clays present are iron and aluminum oxides or a kaolinite, then we end up with a very low CEC, and we call those soils candic. So they have a candic horizon. And usually they're brightly colored because of all the iron oxides that are present. So these generally occur in highly weathered areas. Usually ultrasols is where we see them. And a lot of the iron oxides, they occur in highly weathered soils to a great degree, but they're also present in small amounts in soils in parts of the world that are less weathered. And in those parts of the world, they generally occur as coatings on soil particles, and that's what gives us our reds and browns and yellows. Our last type of colloid is solar organic matter. Solar organic matter includes decayed plant and animal detritus, as well as detritus from microbes and other soil organisms. And the charge in soil organic matter comes from functional groups. So these functional groups include carboxylic groups, phenolic groups, alcoholic groups, and so on. And this charge is pH dependent. So at a low pH, where there's lots of hydrogens floating around in solution, these charge sites will end up being filled with a hydrogen. But if we raise that pH, which means there's less hydrogen floating around in solution, we will deprotonate these exchange sites, and we end up with a negative charge that a cation like calcium or magnesium could absorb onto. So these do contribute a lot of cation exchange capacity, or the ability to hold on to cations, but that CEC, that charge, is pH dependent.